Hello and welcome back to Chapter 7. We're covering plate tectonics. We're going to wrap up this series or block of lectures where we talk about the mechanisms that move plates. This is often referred to also out there in the world of plate tectonics as plate dynamics. It was this issue that really challenged Wagner and Alfred Wagner and his ideas, and it led people to sort of discredit him at first. But as time moved on and we developed ways to image the Earth's interior and to evaluate the behavior of rocks on the seafloor, both indirectly through magnetic surveys, but also directly through drilling and sampling, we've come to rely on a number of processes that likely contribute to moving oceanic plates. But the question of which is going to be the most effective is under debate, is something that is ongoing research. And there are likely a number of processes. These include convection, ridge push, slab pull, and trench suction / rollback, which I use as a kind of combination term here, that contribute in different ways to plate motion. It was Arthur Holmes who came up with plate convection in the 30s as a mechanism to really move the plates, and that involves heat from below and rising rock. Now, it's not rising magma, but it's rising rock. And as you remember from our discussion of plate tectonics, it rises below the ridges and then moves out to the flanks or the sides. And its drag between the moving mantle that's below the asthenosphere to some degree and the crust, or the lithosphere, I should say, up above, that moves plates off to the left. And so that kind of motion is going to involve rise under the mid-ocean ridge. And then you also know that you have plates coming down at your convergent margins, and so you have convection or flow into the mantle at a convergent margin. The concept of ridge push, slab pull, and then these trench suction and rollback have since evolved in the 60s, and really today we hear a lot about slab pull in the literature. Okay, where does this come from? Well, the Arthur Holmes model for convection, you can see here where we've got rising magma. This is actually a hot spot here, but if we put it underneath in the subsurface here in the upper mantle, we can have a kind of convective current where we have subducting plates coming all the way down to the bottom of the mantle. We have rising magmas or rising rocks which undergo decompression melting, and then sinking slabs over here to the right, which are also coming down. But what we see is a lot of mass exchange or vertical mass exchange within this system. So things that are cold or colder, okay, and things that are hot or hotter. And hot stuff is rising, it gets out to the Earth's surface or closer to the Earth's surface, and then it sinks down. And you can see this in like a boiling pot of water. If you put it on your stove, you would see convection going on in those places. But what we found is that in some areas where we have mid-ocean ridges, we also have and we have a combination of different processes that might be going on. We see different velocities in plates. And so it's the plate velocities that kind of lead us to thinking about how different mechanisms of plate motion might be, or how they might be contributing, and to sort of what degree or what proportion of those mechanisms are contributing to any given plate of those 13 major plates that are sort of floating around on the Earth's asthenosphere. So ridge push, if we go out to the ridge here, involves putting gravity to work. And so gravity is sort of pulling down towards the center of the Earth here on both sides of this ridge. But the ridge is sloped, and it's sloped because we've got hot buoyant magma rising up, hot buoyant rock rising up below the ridge. And so anytime gravity is pulling down like this, we're also going to get a horizontal component off of this, which is off in that direction as well, because it's pulling on a sloped surface. Okay? So gravity pulls in this direction, but the ultimate plate motion is sort of down and as well as off to the right. And it's following, I'll make this in red, it's following this red vector that I just drawn on here, right? Parallel to the plate itself. And this one's going to be also down and to the left. And so that's ridge push, right? But the problem is with this is that plates can be thousands of kilometers in width. And so the idea that the ridge itself is capable of pushing all the way, let's say this distance here between the trench and the ridge is, let's say, 1,000 kilometers, which is just an approximation here. The idea that it could be really effective at pushing on a 1,000-kilometer scale seems unlikely, just given the forces that are involved in the amount of rock that's being pulled down and the distances that it's moving. And so another concept is slab pull. And slab pull happens in the subducting slab, which is undergoing metamorphism. As it undergoes metamorphism, it is changing density. It is becoming denser. It is releasing volatiles up into our volcanic arc, which is right here. And so we get volcanic eruptions going on. And as it gets denser, gravity is pulling on it, and it's pulling down. So gravity is doing the work here, as well as metamorphism. And so that is where we have a slab sinking, and we have slab pull going on. So ridge push, that's number one I've listed here. These are not in any particular order. Slab pull is also very popular. Convection, which I talked about, mantle convection. And for now, we'll leave it as upper mantle convection, but there is a relatively vigorous debate as to whether or not the whole mantle, both upper and lower mantle, can convect, or if it's just the upper mantle. And I think the debate is leaning towards upper mantle in general, based on the density and behavior of minerals and materials and the exchange. But you have a number of interesting and conflicting issues with just upper mantle convection or sort of two-cell convection. So we have slab pull, we have mantle convection, and we have ridge push, all working on moving the plates. And it turns out that in plates where we have ridge push and slab pull working together, we find fast plate motion. Okay, so that means at the mid-ocean ridge, we see the fastest spreading rates, greater than 15 to 20 centimeters per year. And where we see the slowest plates, we often don't find that we have push and pull and potentially convection all working in unison. We find that pull has been removed. And so in some places, for instance, in this overlying plate here, in this subduction zone, there's no pull on the plate here. And so even though it may be moving off to our left, it's not really going to be moving quite as fast as the plate off on the plate on the left-hand side, and then the plate on the far left, or I should really say this, the central plate. So we've got, if we want to think about it, we've got 1, 2, 3 different plates here, because there's a plate boundary right here, which is our mid-ocean ridge. And so plate 2 is going to be moving the fastest, at least as we can tell, of plate compared to plate 2 and to plate 1. The final combination of things that is going on here is this trench suction that's going on. As the slab comes down, it is dragging on the mantle, and it is creating a convection current here, and it's creating what we think is a convection current here. And so these convection currents, as the slab sinks, the one in this area on the right, just below the arc, is helping to drag this plate number 1 to the left. And so that is our trench suction. It's getting sucked into the trench on the left-hand side because of this convection current. Another factor that's going on here is something else called slab rollback. And as the slab gets denser and it gets older and colder, it will sink. And as it does so, it sinks back and back. And that means the trench moves back to the left as the slab rolls back, and so that can also cause plate number 1 in this case to move off to the left as well. Right, so we've got ridge push happening at the ridge. We've got slab pull happening down here at the end of the slab. We have mantle convection, which probably contributes to some degree in moving the plates. And then finally, we have this combination of slab rollback and trench suction. The suction is caused by convection currents created by this downgoing slab, and then the rollback of the slab is caused by its sort of aging, cooling slab. As it bends down, and it will pull away from the trench, and as it pulls away from the trench, the overriding plate, which is plate 1 off to our right here, will advance to catch up to it, because we usually don't find open cracks down into the mantle. So the plates, even though they're breaking apart, they don't always give us ever really give us a clear window into the mantle. Okay, so that summarizes the most effective mechanisms of moving the plates. I would say in summary, convection used to be quite popular, and it still is probably an active mechanism, but I think many people are looking to, in the case of subduction zones, slab pull and ridge push as important factors. But each plate is a little bit different and will have to be considered given whether or not it's tectonics, how much slab is being subducted, the kinds of crusts that are involved. So just to summarize, at the end of this particular chapter, we covered plate tectonic theory, which is really a combination of continental drift hypothesis and seafloor spreading. So these two things fit together to make a third thing here. We talked about the anatomy of plates, so the different features we find at the plates, and then finally, what do we think is moving the plates and getting them around? So we'll move on to chapters in the coming weeks. We'll talk about the ocean floor in a little bit more depth, and we'll also talk more in depth about volcanoes. So see you next time.